to tell me where our new curve is centered. So, is it centered here? Is it centered here? Okay, good. Silence is a good thing. That tells me that we're going too fast. What number should you be looking at right now before you look at the p-value? One number I want you to look at. One number. You look at that z. Cassidy asked me that question.
What are you doing wrong since it's invalid?
Turn off all your plots.
Oh.
Hit quit, turn off all your plots, do it again. Look at one number right now. And that one number is not the p-value, but the... Do you remember what this is? You can say no, because it's been almost 24 hours of class time, if you will, since we calculated one of these manually.
Is it how many standard deviations?
Yes! It's how many standard deviations you landed away from zero. Zero being that zero right there. So how many standard deviations are we away?
1.8.
1.8 standard deviations. Which direction? That way. That is your center of your research curve. That's the best. Now, it might be off by a margin of error, but that's the best estimate you've got for where the center of that curve is. So I'm going to go ahead and draw that on this curve, if that's okay with you guys. I'm going to draw a different color too. That is where your data is telling you the center of your curve is. That's where your data is telling you the center of your curve is, somewhere over here. Okay, at negative 1.79. And that's a z-score. That's, as Melanie said, and say it nice and loud with her, it's a number of standard deviations away from that null hypothesis. That's always going to be that. Just so you know, all these things are always standard deviation measures. You are 1.79 or 1.8 standard deviations that way. Now, that corresponds to a percentage, doesn't it? Now, is the percentage important? If you want that percentage, you can simply divide 402 by 590,000 and you'll get that percentage if you want to get it. You don't need to. Articles won't tell you what it is. Not always. Sometimes they will. But you can easily get that percentage if you divided. It would be p hat, wouldn't it? Be p hat. 402 divided by 590,000. And the reason I bring this up is because that's how we originally got this number of negative 1.79. We did that minus that divided by its standard error, and out came negative 1.8. That's how you would do it manually. But we discovered doing it manually is a bit tedious and it gets us lost in the math. Okay, so that's the first thing you have to notice. That's your test statistic. Now remember, from that test statistic, you're going to get your p-value by starting at that test statistic and then shading in whatever direction your research hypothesis tells you to shade. And can you see now why there's so much area shaded? You see now why there's so much area shaded? If you start here and start shading to the right, you're picking up almost the entire curve. That's why your p-value is so damn big. Because it fell, remember the newspaper's claim? The newspaper's claim was that the Florida motorcycle death rate is doing what? What did we just see from our sample data? That it's going down. That's why your p-value is so big. When your p-value is big, big picture here, big p-value, who do you believe? Big p-value, who do you believe? Null or research?
The null.
You believe the null when you get a big p-value. Researchers aren't looking for big p-values. Usually, they're looking for small ones, because what does a small p-value mean? It's an outlier potentially, something changed, right? Something changed with a small p-value. The newspaper wants a small p-value. They want to be able to prove. You see, statistical proof. Boom! Start wearing your helmet, otherwise you're going to die more. Or you're more likely to die, I guess. You can't die more, you die once. Right? So we come back with our data and we go, excuse me, Gainesville Sun, you might want to look at this data because we got a big p-value. Of course you have to explain that to them. What the hell is that? What that means is our data is well within this null hypothesis curve. This null hypothesis curve, remember what this is. This is that the Florida motorcycle death rate hasn't changed. That's what this curve is in English, isn't it? It's the Florida motorcycle death rate hasn't changed. Maybe it's even gotten better, but it hasn't changed for the worse. It hasn't changed for the worse. This is change for the worse. In order for us to believe it's changed for the worse, we gotta land out here. We didn't land. land out there, we landed down here, which is that it's no worse than it used to be. So therefore, that's why our p-value is so damn big. Our p-value is so damn big because our data agrees with the null hypothesis. Blake?
What allows them to make this claim?
Because it's their paper. They could paint that the sky is green if they wanted to, because they're paper. We don't have to buy it. We don't have to buy it. And you can see why they make the claim, because it would sell the paper to you. Especially,
No, not even like a 0% confidence that I would even...
does this surprise you, Blake? That something is pretty with no statistical backing? My friend, we taught you nothing. No, I'm kidding. I'm kidding. It's kind of infuriating to think about it. It's a little bit infuriating, right? Some people will argue, and maybe well, I think, that I shouldn't even be doing hypothesis tests because this isn't sample data, it's population data. The case still holds, doesn't it? If you treat this as population data, forget the margins of error, forget the bell curves, is this number less than that number? Yes, then my case is still valid. That number's less. And it's inarguably less. There's no margins of error to discuss anymore because it's parameter values. So, Blake, I'm with you, brother. I could see the fire in your eyes pop up. You're like, what? I'm with you, dude. It drives me nuts too when I see that kind of stuff. It does. It's frustrating, which is why I like teaching you guys to look for it. I'm not saying everything printed is piss poor. I'm saying it's often piss poor. not to be negative. I saw a hand. Linda, go.
Did they change the law? Did they help?
I don't know. I haven't done any research since then. Anybody been in Florida recently? Ride a motorcycle? We'll Google it at a break. I'll Google it at the break and see.
Wait, what is
The question was, have they changed the law back based on this for helmets in Florida?
They still don't know what's
They don't have to wear helmets in Florida.
Yeah, no.
That's right. So I guess not. I guess it's still revoked. So maybe the political clout the Gainesville Sun has is not clouty enough to win over whatever happens in the capital of Florida, Jacksonville. Is that right? Where's Mick McCann? Where's that geography guy? I'm gonna say it's Jacksonville. I'm gonna make that up right now. It's not Jacksonville. I don't know. Maybe it's Jacksonville. Anyway, regardless, let's finish our tests and then take our 5. We got 2 more steps to do. Because we did our test, we crunched our data, we've discussed what we just found, yes? But now let's make sure we can report it to our neighbor. Report it to our neighbor. Number 1, it appears or does not appear. Oh, the p-value was that, oh sorry, that p-value was that huge 96%. I'm sorry, I got tons. Look at the z, look at the z, don't look at the p yet. I ever told you to look at the p. Yes, the p is a consequence of the z, yes? So once you have the z being that extreme, you realize the p-value is going to be huge. So 96%. We were looking for something less than 5%, we got something greater than 95. Which actually tells us exactly the opposite of what the paper was trying to claim, doesn't it? Because if we had simply changed our hypothesis to less than instead of greater than, this would actually support that, wouldn't it? Because the complement of 96% is 4%, which slides in under 5%. So we can actually not just disprove the paper's claim statistically, we can support essentially the opposite claim in that the rate's actually going down. Kendra, go.
So for the test statistic, would you put p as less than, or would you still put less than or equal to?
For the test statistic?
Ununderstood.
For the test statistic, you're putting this guy. That's the test statistic.
Oh,
That's the test statistic, my friend. This is the p-value.
right.
Yeah, so for test statistic, it's always going to be directly above it, which distribution you choose. It's going to start with that variable, and then whatever that variable equals. And then Melanie's interpretation, it's a number of standard deviation. Don't forget that. It's a number of standard deviation. Don't forget that. That's crucial. You have to have that in the back of your mind. Because the further you get away from 0, the more significant your results are. It's just these results went exactly the wrong way we were expecting. We didn't expect them to go that way. We were trying to get them to go this way if we wanted to support the paper. Kendra, does that make sense?
Yes.
As a perfectly good yawn, I interrupted. I apologize. Perfectly good yawn. Okay, so you're explaining it to your neighbor. You're out there doing yard work this weekend. It's going to rain a little bit, soften the dirt for you. Very good, very good. What are you going to say? It appears or does not appear?
No.
It does not appear that the Florida motorcycle death rate has raised or has increased. It does not appear. It does not appear. FYI, your conclusion is always based on saying something about this number. So generally, when you get a big p-value, you just say it doesn't appear that it went up. It doesn't appear that it went up. Some people will say it appears that it's the same. I mean, that's okay. I got no problem with you saying that. You can say that to your neighbor. But a traditional statistician will wrap you on the knuckles and say,
No, you must say, fail to reject the null hypothesis.
that's okay. You'll hear that from time to time. You just won't hear it here very much, especially on the British voice. Cool? Error possibility? Type 2, yes. Oh crap. Because this was one you guys were so worried about, right? Type 2 was the worst possible. So how do you want to avoid a type 2? You're going to lower that confidence. The thing is, based on the severity of this result, I don't think you're ever going to lower confidence to make that significant. I mean, seriously, look at where it is, right? Look at where it is. It's on the other side of the curve as to where you thought it was going to be. So essentially, the only way this could be an outlier, think of it this way. Actually, I'll put this here, and I'll put this here.
So would they be a type 1?
The only way this would be in, no, you got a big p-value. The only way this could be in error is if the motorcycle death rate did in fact go up and you missed it, right? That's a type 2. You say it's not raised, but in fact it was. So a type 2 would say, okay, there's a research curve out here with a higher rate and we completely missed it. Well, think about that. Think about where your data would land on that curve. It landed down here, correct? It's got to hit there. How likely is that? Call it 0, because it's not going to happen, right? That's the idea. If you missed the raising of the death rate, and it's out there, you'd have to land way the hell left. It's already way the hell left on the null curve. It's going to have to be wayer the heller lefter on the research curve, which makes it exponentially more 0. That was like the worst mathematical statement ever uttered in the history of mathematical statements. But I friggin' love it. I'm glad I recorded it, because it captures it perfectly. If you make a type 2 error, that curve is out there. So it's more extreme to be left on that curve than the null curve. So I would say let's rest our minds about a type 2 error. I don't think it's going to happen. I don't think it's going to happen. Good, let's take 5. The thing turned itself off anyway. It's telling us something. Let's come back and do a different one. Do a different one.